All right, let's go ahead and get started. I got a few more things to cover from the last section, and we'll do with some review, whatever time we have left. Any questions before we get back into this? So last time we set up this integral to find the area under one arch of this. So where we left off last time was, we got this integral here. So from here, if we keep setting it, or if we keep simplifying, we get the integrand of 1 minus 2 cosine theta plus cosine squared theta d theta. So is this an integral that we can do, that we can evaluate? So if we take it term by term, what's the antiderivative of 1? Theta. And then 2 cosine theta. Should be negative 2 sine theta, right? So it's been a while since we've done something like this, but how do we handle this cosine squared? So one of the trig identities we talked about a while ago, and try to sneak it up into the margins here. Cosine 2 theta equals 1 minus, what is it? 2 cosine squared theta minus 1. So we can't really, we have a hard time integrating cosine squared directly, but what we can do is, isolate the cosine squared theta here and get something else. So what does cosine squared of theta equal? Cosine squared theta equals 1/2 times 1 plus cosine 2 theta. So does that seem familiar? I know it's been a couple of months since we've done trig substitution stuff, but we okay with that? Okay. So what is the antiderivative of that 1/2 plus 1, or 1/2 times 1 plus cosine 2 theta? So the antiderivative of 1/2 will be 1/2 theta. And the antiderivative of cosine 2 theta will be 1/2 sine of 2 theta. So I believe this is our full antiderivative. 1/4 sine of 2 theta. Evaluated from 2 pi to 0. Go ahead. So let's just handle cosine 2 theta. What's the antiderivative of cosine 2 theta?
Oh, I get it.
Yeah, so that alone is 1/2 sine of 2 theta. Because I think when we first did that, probably did U substitution or talked about chain rule there, but that's where that extra factor of 1/2 comes from. So now if we plug in all these things, what do we get? R squared times 2 theta. What is sine of 2 theta? 0. Actually, I think any of these sine terms are going to come out to 0, right? So 2 theta, or sorry, 2 pi plus pi. And that should be it, right? I believe I should get 3 pi r squared. So yeah, Phil, ask me whatever question. I know I ran out of space and I kind of crammed a lot of algebra into a very short space there. So do we agree with 3 pi r squared? Any questions where it came from? The biggest thing for me here is essentially what we did yesterday, is setting up this integral. So how do we take a parametric curve and basically set this up as an area integrating on that parameter instead of on x or y? All right. So again, I want to find an area enclosed by the x-axis and the curve given by these two parametric equations. So how can we start setting this up? What kind of information do we need first? So from last time, I'll remind you, this is the integral we're kind of trying to set up. So, which is represented slightly differently, but it's not really different from any of the areas we've set it before. You're going to integrate over some interval in x. You're letting x vary and you're integrating over all the y values. Usually we write that as f of x dx. So do we know any of that information yet?
Can you use just like the y equals?
Yeah, absolutely. So that's part of this. So I'll say t equals b. These are going to be t values when we find them, these bounds. But yeah, that y is my goal here is to represent this not in terms of x, but in terms of t. So 2t minus t squared dx. So that's a good positive first step. So we got to handle the bounds still, and we got to handle the dx part.
Can we just get the derivative of x?
Right. So what is dx dt? 3t squared, which means that I want dx. So dx I can say is equal to 3t squared dt. So getting closer. I think the last thing we have not, so we have an integrand, 2t minus t squared times 3t squared dt. Last thing we need is to figure out what the bounds are. So how can we determine what those are? Where am I finding this area? Like, where is it being described? Enclosed by the x-axis, right? So I don't know what this curve looks like, except I'm looking for this area here. So there's some area between the x-axis and the curve itself. Does that description or does that picture there help us think about how to find the bounds? How can we find them? We set y equal to 0. So if I'm crossing the x-axis, if I'm looking for x-intercepts, I'm looking for where the y value is equal to 0. So if y is equal to 2t minus 2 squared, t squared equals 0. I can factor out a t. So t times 2 minus t equals 0. And that gives me t values of 0 and 2. So I think that is the full integral. I got the interval from 0 to 2. I'm going to do some distributing. So that becomes 6t to the third minus 3t to the fourth. So I'll get in pause there. Like I said, I think the setting up these integrals is probably the more difficult and more important step. So any questions about how we got here based on the information and kind of what I required? If we're okay with how this integral got generated, let's go ahead and compute it. So what's the antiderivative of this function? What happens to 6t cubed? Three halves t to the fourth, and then minus 3/5 t to the fifth from 0 to 2. So I get 3 halves of 16 minus 3 halves of 32. And then if I plug in 0 for t's, those will all be 0. So does this simplify in any kind of convenient way? So 24 minus 96 over 5. Is that 24 over 5? I believe 24 times 5 is 120. Okay, I feel good about 24 over 5 then. Questions? Go ahead.
How do you get the 2/2?
Good question. I didn't say that. Where did 3 over 2 come from? Right, so you see it? You see it? Okay, cool. All right, so yeah, it's probably one of the first antiderivative rules you learned is the basically just turning the power rule around. Any questions here? So what other kind of things we've done with area or with integrals? Also in arc lengths, right? So then the first question I asked you, is this the same curve I showed you before? I think on like the first slide of this section, I asked you if this was a function, right? What was your answer? Or what is your answer now? Is that a function? So I'm purposefully asking you that in a very ambiguous way. Is y a function of x? Now that fails, right? There are lots of x values that give me multiple y values, which violate what a function is. But I can think of this being a function of, for every single t, I can get a single point in x and y. That's a one-to-one thing. So looked at it that way, this is a function. Do we remember how we set up arc length when we were looking in Cartesian coordinates? So basically what we did was we take a curve that has no straight lines in it, and we approximate it, breaking it up into these straight line segments. So let's just pick the first one of these. Can I find the length of this little pink line between P0 and P1? How do I find that length? So I'm going to call this L. So L is equal to what? The square root of some change in x over some change in y. So delta x dt, oh, getting ahead of myself. So delta x squared plus delta y squared. But we're talking about parametric curves, right? So because of that, I'm going to have basically these changes in x and y are going to be functions of, they're going to depend on t. So I'll do this. I want to think of these as delta x over delta t squared plus delta y over delta t squared. But I can't divide by delta t squared unless I multiply by delta t squared. So I'm doing this all in delta, so these are big changes, but if I limit these so that they're going to become very, very small, I can think of these as derivatives. So the way I find an arc length is the derivative with respect to x squared plus the derivative of y with respect to t squared dt. So if you remember the way we set this up for Cartesian coordinates, does this look somewhat familiar? What does the version of this thing look like in Cartesian coordinates? Do you remember? Square root of 1 plus dy dx squared. So the way it's developed is the same way. It's just we're looking at these functions a different way, so our setup's going to be slightly different. So I want to find the arc length all along the unit circle. So these two functions, when you let t vary between 0 and 2 pi, these are going to sweep out a unit circle. And I can't remember if we've done this exact example in here, but one thing I'll remind you of is this. if I draw the unit circle, any point on here, so XY, how are those XY points related to, you know, whatever angle you're looking at, whatever angle projects them? What does the X value come from? What does the Y value come from?
Those are inside.
Yeah, those are cosine of T and sine of T. So those are exactly the parameters that or the parametric equations I've set up here. And probably don't think of the unit circle going this way. We probably think of it, we draw the circle and build up the angles from there. Now we're going to use those angles to build up the circle. So I want to find the arc length along that unit circle. Is that something I really need calculus to figure out for me? What do you call the arc length around a circle? Circumference. How do I find the circumference of any circle? 2 pi r. What's the radius here? 1. So we're going to set this up using an integral, but we should get 2 pi when we're done, right? So let's set this up using an integral. I want to integrate from a to b of dx dt squared plus dy dt squared dt. So we need to start filling in some of this information. So I need to worry about the bounds. I need to worry about dx dt and dy dt.
Bound between 0 and pi.
What do we think? Does that make sense for the bounds? So let me ask this question. What variable do the bounds represent? Like that'd be values of what? T. So it makes sense for me to span the entire T interval that I'm actually asking you about. So yeah, 0 and 2 pi are good bounds. Now how about the other two? What is dx dt? I know y'all know this one. It's one of those. It's negative sign. So negative sine t squared. What's dy dt?
Cosine.
Cosine t squared dt. When I square, what happens? I get the square root of sine squared t plus cosine squared t. Is that an integral we can do? What's that?
So just 1.
Yeah, so that's a Pythagorean identity. So this just comes out to be, yeah, dt. Or if you'd rather, 1 dt. What's the antiderivative of 1? T. Evaluated from 2 pi to 0, or 0 to 2 pi, I get 2 pi minus 0, which is exactly what we knew it was going to be. So any questions on how to set these integrals up? We okay? All right. One more for you. So back to the cycloid. I want to find the length of, so basically, we talked about these things in the middle of Wednesday, but a cycloid is essentially this thing. It's these end-to-end arches that are all supposed to be the same size. So I want to find the length of one of these. So from here to here, I want to find the length of that arch. So how do I set up the integral that does that? R is a constant. Yeah, so basically our length is going to be in terms of R. So how do I set this up from here? Or do you need to tell me first what the integral is we're setting up? What does it look like? How do you know it's from 0 to 2 pi?
Think that other things, but we know it starts at 0 and then 1 round is 2 pi.
I don't think it was 2 pi. So Let's not use our memory. Let's talk about how to find what it is. So I agree that, yeah, this is going to start at 0, but how do we find this other value of theta? Right, so we can set y equals 0. So knowing what this graph looks like, we care about, basically, I just need to find 2 adjacent values where the graph is at the x-axis. I know one of them is going to happen at 0. When's the other one going to happen? If y equals 0, that means that 1 minus cosine theta equals 0, which means cosine theta equals 1, which means Munya was right all along.
Why did you like ignore R?
Here's why. I didn't really ignore it. But I know that R is a constant, right? And I can go a little further. I can say it's bigger than 0. If R is 0, then this whole thing is like not worth looking at. So I can divide by it.
Oh, okay.
So if I divide it away, then yeah, I get cosine theta equals 1. So those are my bounds. Definitely need those. But what's the function I'm going to integrate? Dx over dt. What was that, Saul?
And dy would be, but under radical.
Okay. So the square root of dx dt plus dy dt.
Squared.
Okay, good. Yeah, I need each of these to be squared. So let's go for that. What is the derivative? Yeah, let's do some scratch work over here. What is dx dt? Keep calling it t. Dx d theta and dy d theta. So x is defined up here. R times theta minus sine theta. What's the derivative of that with respect to theta? R times 1 minus cosine theta. And how about dy d theta? R sine theta. Okay, so if I square these things, I should get r squared times 1 minus cosine theta squared, plus r squared sine squared theta, all under a square root, times d theta. So again, I think the setup is the newest thing here. Are we okay with this integral, how it got built? If we're okay with that, is there anything I can do to make it easier to handle? I think I can take an r out, so let's do that slowly.
We just pick out square root R squared.
I'm going to take out a square root of r squared, and then what's left is 1 minus cosine theta squared plus sine squared theta.
It's 3 to 5, 1 minus cosine squared. Yeah, no, you have to expand it.
Yeah.
And then you can.
So let's expand it and see if anything convenient happens for us. So 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta d theta.
So the 5 to 1, like cosine plus 1. So it'll be those 2 minus 2 cosine.
Okay. Yep, 2 minus 2 cosine theta d theta. And because I wanted review some stuff. I want to give you a chance to ask me questions about anything you want. I'm going to go ahead and stop there. So I believe you could find a calculator to compute that integral for yourself. But then the setup again is the more difficult, more important step for me. Go ahead.
This will be on the next.
This concept, yeah. It'll be an integral that's more accessible than that if you see it. This gets a little more involved than I want to spend time on right now. Questions about anything before I close out? Okay, so we got about half a class left. Any questions about the test or the things that are going to be on it?
Section.
8.4 to 9.2. So basically, like a lot of stuff having to do with infinite series and Taylor series, all that kind of stuff, and then the last 2 units we did on parametric curves. Go ahead.
On the practice group, it doesn't tell us if we got it right or not.
Oh, really?
Yeah, just gives us the point we answered.
Oh, whether or not you, yeah, I can look at that. I'll make sure.
And can we also go over conditioning versus spousal condition?
Yeah. Do you have a specific example, or should I just?
No.
Okay. Trying to think of one that I haven't already talked about, but let's do so I want to describe this series here as, basically I have 3 options at this point. Diverges, converges conditionally, converges absolutely. So how do I start ruling things out, or how do I start answering that question?
Who needs a ratio?
I don't think the ratio test is going to do much for me. I believe the ratio test will give you a limit of 1. So ratio test, I don't think is going to give you a conclusion there. What else can we try? We can try the alternating series test. So how does that work? Okay, so I have an alternating component. And then what'd you say the other part was? Is not root n. Root 1 over root n. Okay, so B of n here. So I have an alternating part. Now let's look at the non-alternating part. What do I want to know about this B of n, the B sub n? Is it positive for all n? Okay, good. So it is positive. What else do I care about? Is it decreasing? And what else? Yeah, I need to know something about its limit as n goes to infinity.
Does it go to 0?
Does it go to 0? Does it go to 0? Absolutely does. By the way, something we haven't talked about, but I'm not going to save you a ton of time, but is it so if I have a sequence that's positive, but it's going to 0, is there any way for that sequence not to be decreasing? So there might be a little bit of redundancy here, but that's okay. I don't think it took us that long to answer all those questions. So we found all the conditions that I think we needed to find. So what does that tell us?
Convergent.
It converges how? Do we know it's conditional? I think all we know right now is that it doesn't diverge. It converges in some way. It converges conditionally, but we might be able to say that it converges absolutely as well, right? So still got a little more work to do. So how can I tell if this, so definitely converges at least conditionally. So how can I tell if it converges absolutely?
Ratio.
The ratio test is still going to give you 1. So I'll go ahead and do it since you've probably not seen it happen. But if I do the limit of 2 consecutive terms, that ratio, -1 to the n+1 over radical n+1 times -1 to the n. So the absolute value is going to kill the alternation, right? So the limit I really get is radical n over radical n+1. So as n gets very, very big, those are going to get closer and closer together. So that's going to go towards 1. So ratio test doesn't help. But let me ask this question. If I'm looking at, what does it mean for a series to be absolutely convergent?
Whether it's positive or negative, it's still less than 1.
Not that it's less than 1. So let's talk about, do we remember what conditional convergence means?
Just when that series converges, but it's absolutely not.
Right, and that's the big difference here with absolute convergence. Instead of looking at the series I gave you, I want to look at this series where I take the absolute value of all the terms. What does the absolute value do to this series? It takes away the alternating behavior. So now what I have is essentially is this series. And I think we already agreed that radical n is going to be positive all the time, right? So I can just rewrite this as 1 over radical n. So now I'm talking about whether or not this thing converges. The series of 1 over radical n. Do we know what that does? But why does it diverge?
If the 1 over n to the p, as long as
Right.
p is greater than 1, then it converges. Otherwise,
Right. So we call that the p-series test. 1 over n is kind of the boundary case. 1 over n diverges, but anything larger than it converges. I'm sorry, any power larger than 1 converges. 1 or lower diverges. So the absolute value of that series diverges. So what does that teach us? That teaches us that we have conditional convergence. So the series as written converges. But if I try to add up all the absolute values of all the terms, it fails to converge. So when it's allowed to alternate, it converges.
So does the series only work if it's like 9 over?
I mean, it can be. I can tell you something about that as well. As long as it just has to be a constant over.
Could it be like n squared plus 2 or something like that, or is it just?
Oh, so that's a good question. So let's talk about that. Do we think that converges or diverges? It should converge, right? I know that 1 over n squared converges, right? Which means if I make the denominator even bigger, it'll still converge. But even this thing, I know that 1 over n squared converges, but even if I make the denominator smaller, in that way, it'll still converge.
If the exponent has to be less than 1, it gives you.
Bigger than 1 to converge.
I'm gonna ask the same thing.
Yeah, so
If it's a plus number or minus number, we kind of neglect it, right? Because like once you get into really big numbers.
yeah, if it's a constant, it gets overwhelmed. But yeah, the p-series, so what does the p-series look like? I'm writing this in the simplest way. So 1 over n to the p, but really I can add constants to the denominator. I can have a constant in the numerator. Doesn't really change the behavior of this, but I think we talked about this series a while ago, that even though this sequence goes to 0, the series diverges. So the way that one way I kind of share with y'all to think about it is that if this thing diverges, then anything that grows, anything that decreases more slowly than that is going to diverge as well, right? So 1 over square root of n has to diverge. But if I have something like this, 1 over n to the 1.1, that's going to converge. As long as I'm anything larger than 1 is going to converge. Go ahead.
The alternating series test, are we looking at Bn? or
Only that.
Just Bn?
Yeah. But here's the thing. You're looking, so the test itself, like most of what we're focusing on is the non-alternating part of the series. But this test only works if the overall series alternates. So like, if I don't like,
It was like 1 to the n over square root of n. It doesn't really say.
okay, so if it was just 1 over square root of n, then yes, all these things are still true. It's positive, it decreases, its limit is 0. But but the series itself doesn't alternate. So really what we do here, kind of like mechanically, we make sure that there is an alternating component, but then once that exists, we kind of just move on. We move on to the part of this that doesn't alternate. How we doing? Okay. What else?
Can we go over how to find the power series representation of a function?
You got an example?
Yeah, f of x equals x over 1/2 minus x.
X over what?
1/2.
Minus x? Okay. And we want to turn this into a power series? Okay. So we've talked about lots of ways to get that done. There's the Taylor, maybe not lots of ways. Maybe it's just the Taylor series and the geometric series approach to this. Does this jump out at you as?
Can we rewrite it because of that?
Yeah, so it sounds to me, since you want to focus, since you're focused on this 1/2, that suggests to me that you're trying to go the geometric sum approach here. So what do you want to do with that 1/2? Multiply by 2. So what I'm going to do is I'm going to multiply numerator and denominator here by 2. And what do I get? I get 2x over 1 minus 2x. Does that make things different? Does that help?
The 2 x's don't cancel out.
The 2x's do not cancel out.
No, it's in the form, so we can start like finding our terms.
Right. So the sum of an infinite geometric series is this first term over 1 minus common ratio. I think we kind of have that. We have a first term. We have a common ratio. So what is our first term then? And common ratio is? Okay. So we want to turn this into a power series. So where do you want to go from here? Do you want to build a few terms and try to generalize it, or do you want to just jump straight to the generalization? You call it. Let's do it. So I keep putting n equals 0. Is that really, I maybe assuming too much? What do we want to start with? N equals 1. Okay. All right. So what's the rest of this generalization look like?
Yes.
Not x. Let me just rewrite. From n equals 1 to infinity, 2x to the power of n. Are we okay with that? First term will be 2x, second term will be 2x squared or 4x squared, then 8x cubed. Is that the behavior we want out of that? I think it is. So that looks good. since we came up with a power series, we should probably also talk about how good that series is or where it converges. Where does this thing converge? 1/2? What about 1/2?
Or what says it on here?
Okay. And that's one thing I wanted to talk to you about based on me looking at your homework last night is there seems to be some confusion among a few of you, more than a few of you, about radius of convergence, interval of convergence. So let's talk about that. Can I find the radius of convergence of this series we just built? So we are using a geometric series here. When did geometric series converge? When the ratio is what?
The -1 and
Between -1 and 1, or when the absolute value is less than 1. Common ratio for us is 2x. So what can I say about the radius?
1/2.
So this right here is my radius of convergence. So as long as basically, I'm not really telling you where my center is. I'm just telling you that as long as I'm within half a unit from that center, the series will converge. So what does the interval of convergence tell you that the radius of convergence does not?
If it converges independently.
Tells you like where the bounds are. So let me give you an example that's not related to this, but if I tell you the radius of convergence of a series is 10, can you tell me any x value where it converges? You can't really tell me for sure because I told you how big the radius was, but I didn't tell you where it was. So the interval tells you where those values are. So in this case, they're between the x values between -1/2 and 1/2. On the written homework, I just graded the one question where that was really relevant was I have to do a power series for natural log of x, but it was centered at x = 5. So a lot of you, a few of you told me that the radius of convergence was 5, which it was, but told me that was between -5 and 5, which is not possible. So the radius does not tell you the interval of convergence, but you can kind of determine what the radius is from the interval. So I would call this the radius of convergence, and I would call this the interval. Go ahead.
Is the radius of convergence technically only like the number 1/2?
It's a number 1/2, yeah. Another thing I wanted to bring up. I did not check the endpoint before I boxed this in. Do I need to check the endpoints here? In general, you should, but for your geometric series, we kind of have a shortcut. We don't really need to. One thing we've talked about is if we have a geometric series with a common ratio of 1, it will not converge. Or -1, it will not converge. So for geometric series, I know that those intervals are very strict. I can never include the endpoints. But in general, like the one from the homework I just brought up, the natural log one, I think you needed the ratio test to find that radius of convergence, which means that's not a geometric series. So you can't really take that liberty. You can't really take that shortcut. You really do need to check the endpoints.
Always use raise or convergence, right?
What do you mean always?
Not the raise, the
Ratio test?
ratio test.
Yeah. So you can always use it. I won't promise that it'll always tell you something. Like I think the last example we just did, it did not.
To get the radius. Even if it's geometric series, it's supposed to give you the same thing, right?
It better, yeah. So yeah, if you want to do the ratio test with this, we only have 5 minutes, so I'm not going to do it, but I'll post these whiteboards. You can definitely do it. You better get the same number. What else? Go ahead.
Is there any questions about like estimating a value using the first 3 terms or?
I wouldn't count on it. I mean, those.
They're long.
Yeah. So I mean, again, you got 50 minutes. Web work, you have more than 50 minutes, hopefully, to do this. So, yeah, those things are like they're way less about conceptual math and way more about you plugging stuff into calculators, which is not what we're here to prove you can do.
How many for your response is there?
I think it's the same format as last time. So 10 multiple choice, 2 free response. Was that?
Yeah.
I don't think the first test was that way, but I know the last one was. Okay. So I think, yeah, same format. What else? Go ahead, Colin.
So when differentiating or integrating power theories.
Yeah.
It's meant, like, the purpose of doing that is to get it into a more manageable form.
Yeah.
Right, and then Taylor series is not that, like, so like when we would differentiate a series. We would then we differentiate it and reintegrate it to get it back.
Yeah. Mhm.
We don't do that with Taylor series.
No. So let me give you an example here. So one, I think this come up somewhere either in my examples or the homework. This kind of series here. There's no way to make this look like a geometric sum. That's not possible. But what I can do, if I take a antiderivative of this, I get 1/1 minus x. Is this thing geometric?
Yeah.
So that is, I think that's the most basic one. This is the 1 plus x squared and so on. So, but if this thing is the target, if I want to make a power series for this, the 1/1 minus x squared, can't really do that using geometric series for this. But if I take the antiderivative, that's pretty simple. And then I just need to take the antiderivative of this thing to get back to where I want. Yeah, sorry, the derivative of this. So yeah, basically you have to undo whatever you did. But we did all of those techniques before you had Taylor series at your disposal, right? If you wanted to, let's say I wanted to build a Maclaurin series around this, then I could find what's f of 0, what's f prime of 0, what's f double prime of 0, and build it up that way. You'll still get the same series. So, and one thing I've said before, but it's worth repeating: powers, like if you have a function, its power series representation is unique, which means no matter how you find it, as long as you do it correctly, you should get that. So they're kind of like derivatives, or they're kind of like derivatives. You have probably a dozen rules for finding derivatives, and no matter which one you use, you should get to the right place. You should get to the same place. So power series are very much the same way. I think basically becomes an issue of you deciding which one makes most sense to you, which you're more comfortable in doing correctly, that kind of stuff. What else? Okay. If there's nothing else, I won't keep you. One thing I do want to say, Alex, I messed up last time. The final exam is not on the 7th of December. It is on the 5th, which is a Tuesday. So I made an announcement. I'll remind you more as we get closer, but all right, have a good weekend, everyone.